system ready, and then you concentrate on developing the data units and control units to process the data. And the third part is the interfacing. Once your number system ready, then the processing units are also ready. Without having the interfacing, we cannot have a complete system. So the third part will be the interfacing and some other optimizations and some peripherals you add to improve the various performance aspects of the system. Okay, so today we are going to start with the second part of the syllabus. That's your the design of various basic units like data, how you control the data flow, and how you control the operations by the control unit. All these things comes under your second part. And also we see how do we generate different control signals, because when we design the control unit, naturally it's the duty of the engineer to ensure that the timing and the sequence is maintained for every operation by the control unit. That means you generate or you enable and disable the right control signal at the right instances. Okay, only then the functioning of the system can be achieved 100% right. Okay, so we start with the flow first. Only when the data is available, these control signals you generate have some meaningful operation to do it. If the data is not available, simply generating the control signals is not going to add any function to the system or value to the system. Okay, so we start with the data flow. How do from what are all the situations the data flow required, from where to where, and how do we manage those data flow. Okay, that's where we are going to start. So the fundamental concept in the data flow is the first starting of your second part of the syllabus, right? What you are seeing here is the simplest bus organization, right, to provide the data flow to different parts of the unit, right, for different functions. When we say simplest, naturally it has only one sorry, it has only one bus. Yeah, it has only one data bus. Okay, with when we have multiple bus, the function becomes very time effective, right? But the cost gets increased. Okay, so when we say simplest, naturally the design complication also won't be there, and the cost also will be less. Okay, so we have a single bus organization here, right, where this is the data bus what we are having, which naturally connects all the places wherever you can store data. Okay, so that when you need data from one place to the other place, you will be able to carry from you will be able to transfer it from the source location to the destination location. Okay, so to start with, we start from the top left register, where you can see that it's written as PC, right, program counter. Any idea what is the use of the program counter? Anyone? Yes, Aditya. Aditya.
Points to address of next instruction to be executed.
Very good, Srivatsan. I'm asking to know, for me to know whether you know the things, or I have to say these things, the basics you might have read. learned already in some subject, and some might not. I'm not supposed to work with the assumption that you know it. Okay, so program counter naturally has the address, right, which points the location in the memory from where you have to take the next instruction for execution. Okay, so once you have taken the instruction and given for execution, program counter has to be naturally, most of the cases, assuming that consecutive instructions are executed next, the program counter will be incremented. Okay, when we have the conditions and loop and all, the program counter has to be slightly modified. Okay, so other than program counter, one other basic registers which is required is the instruction register. Okay, can anyone give me the purpose of instruction register? The purpose of instruction register, can anyone tell me? Samyukta?
To store instructions.
When and from where? So instruction registers, have you people heard of it or not?
Yes, ma'am.
Okay. So instruction register is where the current instruction for execution will be stored, right? Your program counter points the location from where the next instruction to be taken, and whatever the instruction currently being taken from the memory and ready for execution, that is getting stored in the instruction register. Okay, all complete combination of ones and zeros. Then the value in the instruction register will be taken by the decoder, right, to decode the combination of ones and zeros and identify what operation needs to be done, okay, for that combination of ones and zeros. So program counter will be pointing the next instruction to be executed, and instruction register will be giving you the current instruction what is to be executed. Okay, other than that, in every controller and processor, you will have a set of general purpose registers, okay, for storing the data during the process, right, and the temporary results also, right. You may be doing a calculation, in between you will have some result, but that may not be the end result. For example, when you implement an FFT, you want to find one to find one coefficient itself, you will be having you will be doing number of multiplications and addition and subtractions, right. So whatever the result getting generated in between, those results are not the final results, but you need them till you generate the final result. Okay, so kind of results will be stored in the general purpose registers, where you can see that it is from R0 to Rn minus 1. This n will be different from each processor and controller. Some may have 8 general purpose registers, some may have 16, some may have 32, some may have 6, and some may have only 1 or 2 registers. Okay, so that will be changing. Okay, and other than that, we have a set of temporary registers, which is indicated here as T and P, where these registers are accessible only by the controller or the processor. It is not available for the user. Okay, for example, in the general purpose registers, you can use any of these registers whenever you need it. Okay, for storing the information, or to store the result, or to give the source operand, For all these things, you can use those general purpose registers. But when it comes to TEMP, the temporary registers, it is available only for the processor or the controller for its internal functioning. Okay, when you give, for example, swap two values, right? Swap two register contents. In that case, what will happen? If you want to swap the register content R0 and R1, right? You know that first any one register value should be moved to some other location. Only then the next you can move to the one location, then you can copy that, right? So you need a temporary register here, right, where for example first R1 moved to the temporary register, then R0 moved to the temporary register, then R1 moved to R0. This is the first step, this is the second step, then the temporary register value gets moved to R1, right? So now at the end you can see that R1 is in R0 and R0 is in R1. Okay, so for example I'm saying this is one simple example where you require a temporary register. Okay, for like this, when performing different operations, the control unit and ALU requires a temporary register. Okay, and for those operations only it is available. It is not available for the user at all, not accessible at all. That means not addressable. Like you in the instructions you give move R1 comma R2, you cannot find any instruction to use the temporary registers in the instructions. Okay, that means they are not available for the user. Okay. So other than these general set of registers, we have one dedicated register here called Z to store the result. Always any operation performed by the ALU. Some example operations given here like add, sub, and all arithmetic and logical operations obviously included. And when it is addition or subtraction, you get carry also, right? This carry in can be used for borrow in also during the subtract operation. Okay, so whatever the arithmetic and logical operation carried out here, the result is stored only in the Z register. Okay, from the Z register only it has been given, right? If you want to store the result in the memory, it will be given through the internal processor bus. It will be given to the memory, or it will be given to any one of the registers where you are asking it to store. For example, if you are asking the result to be stored in R5, then from Z through the internal bus it will be given to R5. Okay. Same way to give input to the ALU also. For most of the operations other than not, okay, invert operation, for all the other operations minimum 2 operands will be required. Okay, so you can see that there are two inputs to the ALU. One is A and another input is B. Okay, so for example, if I give add R1 comma if I'm giving instruction add R1 comma R2, right? Like that, if I give R1 value and R2 value should be added, and result you can decide where do you want to store the result. And in ARM I think you learned both thumb and ARM instructions, where in case of a thumb instruction you need not specify the destination, where one of the register itself will be taken as a destination. Okay, so these things are all depends on what exactly the instruction set specifies. Okay, so when I want to add R1 and R2, R1 value will be given through one of the inputs to the ALU, and R2 value will be given to one of the registers through from R1 will be given through one of the inputs to the ALU, right? And R2 will be given through another input to the ALU. Through the internal bus only everything takes place. Okay. Uh, now in this, if you observe, one input directly given, right, that is B directly given from the internal processor bus. Okay. But another input, you can see that there is a mux to decide, right? One is through the internal processor bus you get the data, so that can be from anywhere, right? And another input is constant 4. Okay, this is required because when it is some other operation, for this case add r1 comma r2, r1 can be given through y, right, and then given to input a, and r2 can be given through the internal processor bus, r2 can be given to b, and then the ALU does the addition and the result is getting stored in z. Okay, but the same case when you want to simply, once you have taken the address from the program counter, right, which will be pointing the next instruction to be executed, then you have to increment the program counter to point to the next location. Okay, so that the every time you look at the program counter, it will be an updated value from where you have to take. Otherwise, what will happen? You will be taking the same instruction again and again and executing it. Okay. So for that operation, if it is in case of an incrementing the program counter, this input will be chosen instead of y. Okay. Program counter will be given through B input. Okay, and then the constant 4 will be chosen. So program counter value will be added with 4 and the incremented result through Z again stored in the program counter. Okay, we are doing here increment by 4, assuming that it's byte addressable memory, right, and the instruction is of one address is of 32-bit. Okay, based on those things only we give here as constant 4. Okay, if it is thumb instruction, you know that it's only 16 bits. In that case, this increment need not be 4. Either you can increment by 2 and take each instruction, otherwise increment by 4, read the whole instruction, take one part, execute first, then take the next part of the instruction and execute it. 132-bit in case of thumb instruction will be giving you 2 instructions. Okay, so you read the the whole 32-bit at a time, then you take the first 16-bit instruction and execute, and then take the next 16-bit instruction and execute. That way also you can do the operation. Okay. So here every time it will be selected whether it's the normal operation which has been carried out from any one of this, or it's simply adding the program counter by 4. So in that case, this constant 4 will be chosen and given as the input to the A input, or in other cases where it's two different operands, not increment of program counter operation, then the value of y will be chosen and given as the input to the A of the ALU. Okay. So just take 1 minute, recollect whatever I told you till now, right? And then we discuss one other remaining part in the organization. And while going through it, you have some doubt, you clarify then and there and then understand. You have any doubt or we proceed?
You can proceed.
Okay. So now all these are the basic flow within the processor, okay, or within the controller, where either between the registers you transfer the data, or you increment the program counter by transferring its content to the ALU and again store the incremented value back to the program counter. Or once you get the instruction of what the operation needs to be done, you move it to the instruction register. All these are within the processor or within the controller. The data transfer takes place. Okay. But the main source of data for us is the memory. We cannot store the program or any data within the available registers. You know that here sometime maybe 8 register or 16 general purpose registers. With that we cannot hold all the data, right? And the program also, yeah, it will be number of lines, right? It depends on how many instructions it has. Only we call it as a program or software or OS, like that we categorize, including the RTOS, which is the real-time operating system. So that means we'll have more number of instructions in one, even if we take as the basic term, which is the program, right? We'll have number of instructions, right? So naturally we cannot store it within the processor or within the controller. Okay, so we go for additional storage unit, which is the memory here. Okay, so all the program and data are all stored in the memory, and we access the memory and get the data whenever we require. Okay, so for that always the operation will be through these registers only. Okay, from the processor and controller, any data required, right, or any data you want to store it in the memory, right, whatever be the memory operation, the access to the memory operation is only through the memory address register and memory data register. Okay, MAR stands for memory address register and MDR stands for memory data register. Okay. So for any of the operation, whether it is read or whether you want to store some data into the memory, or you have to read some data from the memory, we have to specify from which location of the memory you need the data. Okay, sometime first you give the address and then you say what operation you need to do, right? You give a location address, right? And then from that location, whether you want to store some data into that location or you want to take the value from that location. Okay, that is your, whether you want to read the data or you want to write the data into the memory. Okay, that you have to specify. So once we load the address in the memory address register, and then we say whether it is a read operation or write operation. Okay, which defines the data transfer happens in which direction. Okay, if it is a read operation, that means it is from memory to the processor, the data is getting transferred, right? And if it is a write operation, that means from the processor the data has been given to the memory. Okay, so whatever be the direction of the transfer, everything should happen only through everything should happen only through the memory address register and through memory data register. So in case of a read operation, we specify the address in the memory address register, we enable the read signal. Then once the once the memory location has been identified, the data from that location has been sent to the memory data register. Okay. So in case of memory write, right, we load the address in the memory address register, and in case of a write operation, you want to store some data into the memory. That means we only have to give the data also. Okay, so we give the address in the memory address register, and we give the data in the memory data register. Okay, and then we specify that it is a write operation. Okay, then the data will be, the location will be selected based on the given address, and then the data in the memory data register has been moved to the selected location. Okay, so that's how the write operation takes place. Now for all these operations to be carried out, right, when the write should take place, when the read should take place, all these are going to be defined by the control signals. Okay, are the enable signals. Okay, for example, if you want to load the instruction in the instruction register, it has to be enabled, right? It's a one direction bus, right? And for that it should enable that it should be latched, whatever the input available through the data bus, there should be a provision to latch it to the instruction register. Okay, same way if you are moving some data from R0 to R1, right, the output of R0 should be enabled, and then input of R1 should be enabled. Okay, only then the data in R0 gets latched with R1 register. Okay, like that for every register the control needs to be given. The enable has to be enabled and disabled at the right time. For that, each of these registers have control signals, right? Each register have two control signals, in and out if it is bidirectional data transfer, right? The address, memory address register and all single direction only. The memory is not going to give any address. Okay, only the address will be given from any of the, either from the program counter, or if we are looking for some data, any of these general purpose registers will be giving the address from where we can take the data. Instead of R1, R2, if it is R1 given in bracket, that means the content pointed out by R1 register. This is not representing the data here, this is representing the address here, right? In that case, the content pointed out by R1. So R1 data should be moved to the memory address register and then the value pointed out by R1 should be taken, and then the addition should be carried out. Like that only it functions. Okay, so here the address always given from the, it's a single direction, because address, memory address we only specify, right, through any one of the register, depends upon the operation. Okay, so the memory address register is a single direction, right, one direction register, and the remaining all registers are all bidirectional, because in case of MDR you can see that in case of store operation or write operation we give the data, and in case of read operation the memory gives the data to the memory data register, and from there we are taking it and using it. So it's all bidirectional, right? Same way Y, Z, all these are single directional registers, right? I mean Z is bidirectional, but for in there is no need of any control. Out requires the control, but the in, which is from the ALU, once the operation over, it straight away loads. Same way here, Y out may not require a control, because select is here, which decides what signal should be given to the A input. Okay, so naturally here you don't require additional control. Okay, some in multi bus organization, there is no control for, there is no Z register at all. And in single bus organization, there is control to Z, but there is no control to Y out, because here the additional control is available here in the marks. So there the additional control has not been given. Okay. So this is the overall flow, right? Each and every operation, how it works and how it controls, right? And in case of MAR, MDR and all, additional control signals will be required. Other than all these control signals are called as in and out. Okay, or if in case of in enable, it's called R0 in, right? If it's case of out enable, it's R0 out. That's how the control signals are named. But the memory address and memory data registers may require additional control signals. So all these control signals in detail we will discuss in the next session. Also, how when do we enable what control signal to achieve particular operation, that also we will be discussing in detail. Okay. So now you have few more minutes, right? And you can go through the single bus organization, and have any doubt you can clarify. And please ensure that don't take every session 10 minutes to join this class. Okay. Attendance I'm anyway taking, and I'm going to update the same thing only. But you are losing, that is not proper. That only I'm requesting. So go through the single bus organization. We will discuss the additional control signals in the next session. You have any doubt in this, you can clarify, or you understood also, you have to tell me rather than simply making me wait.